So we will start today's class. So anyone would like to recap what we did in the last class? So anyone would like to recollect? So in the last class, we were dealing with data preparation. Under data preparation, we saw several types of data. And we saw about PCA, how to organize image for PCA. We saw a lot of transformations. Am I audible? Is Srinath, am I audible?
Yes, ma'am.
Yes, you're audible.
Thank you. So we saw a lot of transformations, and then we looked at data augmentation. So why we did all these things is because we know data science is garbage in and garbage out. So whatever data we give, we have to clean the data and give. So we saw how to do that cleaning, and we also understood the various categories available in the data and the various transformations which could be applied to the data. So this is one part. In today's class, what we will learn is that we will learn about classification. So what is classification generally? If you look at, if you have an input data, we need to assign this input data a label, one or two labels to it, one or more labels. We have to assign it to the input data. Suppose you have a photograph. So we need to describe who the person is. That is assigning a label for this photograph. So classification, how it works is, so you have the list of categories within the classifier. So you will take this input. Suppose if this input is, it's a cat picture. So you have a number of classes called cat, dog, buffalo, and so on. So what we will do is that we will take the picture of the cat, compare it with all the categories, and then select the most probable category as its label. So this technique is called as classification. So am I clear what is classification? So it is an important application in machine learning. So it involves looking at the set of inputs. Any questions? So it is an important application in machine learning. So it involves looking at the input and then comparing it with the list of possible categories and then picking up the most probable category for the input. And this process is called as classification. So suppose we might have pictures of animals, pictures of different furnitures. So just by looking at the picture, we need to label what class it belongs to. So sometimes what happens in a picture, you will have two objects. So you can have a tree and you can have a tiger. So we may not know which category it will fall because we have two objects in it. So it is reasonable to give two labels to this one, tree as well as a tiger. We have to give both the labels to this images. So in that case, what we will do is that, so for this class, we will assume that there is only one dominant class per image for understanding. But it is possible to have more than one category in an image. So you have an image. So if you give a label to it, if an expert is giving a label to it, it is called as ground truth. So you have a tiger image. If an expert is labeling, this is a tiger image, this is a malignant tumor or a benign tumor. If an expert is giving that label, it is called as a ground truth or expert label or simply label. So the one which we predict after the comparison with the list of categories is called as predicted value. So to the input, the label is called as a ground truth. The one which comes after the prediction is called as a predicted value or predicted label. So the goal of training is to match the predicted value to the ground truth. So this has to match the ground truth value so that it is
Man,
am
you
I
are mute.
audible?
No, no.
Am I audible now?
Now is you are audible. Yeah.
Okay, thank you. So So in this class, what we will do is that we will just familiarize ourselves with the principles of classification so that later when we deal with the algorithms, it is helpful to understand these concepts. We will also see about clustering. So
Excuse me, man. This is Mahesh. One doubt. So the
yes,
input
sir.
you are giving is ground truth. The ground truth we already know that's the reality. Then why do you need to have prediction?
No, no. To train the model, sir.
Oh, so train the model.
To-
Yes. Okay. 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 Got it.
Yeah.
Got it.
So uh, so we are here at clustering. So what we will do in the clustering is that we will find useful ways to group the samples together so that they don't have labels. So, so clustering also we will see a bit briefly about clustering in this class. So we will see about first we will see about 2D binary classification. First we will see what is binary classification. Suppose you have an input. So if the input will belong to one class or the other class, only two classes can be assigned to this input. Then it is called as a binary class. Either it is one or the second one, only two classes. So the classification is called as binary classification because the labels are, the output categories are only two. Only two classes can be assigned to this input. So it is called as binary classification. Then why do we call it as 2D binary classification is that each sample will have two features. For example, X and Y axis. So X and Y values or height and weight measurement. So it has only two features for every sample. Then it is called as a 2D classification. So 2D binary classification means a sample which has two features and which has two output labels is called as 2D binary classification. Is it clear? There are only two possible labels or classes for every input. So we call it as binary classification. And the system will have only two-dimensional or it has only two dimension of points. So this is referring it to 2D binary classification. So there are several techniques in it. The first set of technique in 2D binary classification is called as boundary methods. Is it clear what is classification? We saw binary classification. There are several techniques in it. The first technique which we will see is about boundary method. So what is boundary method is that, so the data points will be lying in the two dimension. So we will draw a line which separates these two classes. So either this class or this class. It is a binary classifier. So we have two classes. So there is a boundary which separates these two classes together. One samples, all the data points of one samples will lie in one side of the boundary. All the other samples of the other class will lie in the another side of the boundary. So we are a boundary line is used to separate these things. So this technique is called as boundary methods. So this is the important goal is to identify the simplest boundary shape, which can still find a good difference or still split these two classes into two groups. Let's take one example. Let us assume there is a farm which has lot of hens with egg laying hens. So the eggs can be fertilized eggs or unfertilized eggs. So it can have two classes. namely fertilized eggs or unfertilized eggs. And the eggs can have the features like length of the egg, weight of the egg. So it has two features. It has two features and two classes. So how we will create the ground truth for this one is that the traditional method is called as candling method. So what is candling method is that it is just for your information. So we will take the egg and then keep it in front of a candle or a bright light source. If based on the dark fuzzy shadows of the egg, one can understand that whether it is a fertilized egg or an unfertilized egg. The person who is doing this candling method is called as candler. The person who is skilled in doing the candling is called as candler. So we use the candling method to give the ground truth to the eggs. So here our sample is egg and the classes are fertilized and unfertilized, and we use a categorizer or a classifier to classify an egg sample based on these features into two classes, whether fertilized or unfertilized. So the ground truth is given by the candling method. So our categorizer should do the job of candling, saying whether it is a fertilized egg or non-fertilized egg based on the input features. So is it clear? So we have a classifier. So we give the sample, example. So it has two features, feature one and feature two. So based on this input feature, it has to divide into two classes, whether it is fertilized or unfertilized. So it has to do the job of candling just by looking at the input features. For now, you don't ask me that whether we can identify an egg based on the features, but we assume that with the help of these features, we will be able to categorize it into fertilized egg or unfertilized egg. So this is the problem which we have. So let us assume for a moment. So we have two features. One is weight. The other one is length. So we assume that let this circle be fertilized eggs. Then triangle be unfertilized eggs. So we have a distribution of data like this, fertilized eggs and unfertilized eggs. So what we will do is that we will draw a line which separates fertilized eggs with the unfertilized eggs. Here the circle data points are fertilized eggs. These triangle data points are unfertilized eggs. So each egg is plotted as a point given by its two dimensions, that is weight and length. Before itself, I told dimensions means features. So we have two dimension here. So we have two features. So based on these features, these data points are plotted and we use a line, boundary line to separate both the classes. So with this data, we can draw a straight line between these two groups, which can separate fertilized eggs at one side and unfertilized eggs at another side. We are done with the classifier. Our classifier is doing a good job in separating fertilized eggs at one side and unfertilized egg at another side. Now let us assume that so we know these are fertilized eggs, these are unfertilized eggs. So now let us assume that we have added some more chickens in our farm. So the fertilized eggs and unfertilized eggs also increases and the distribution is also changing. So now if you look at it, now we want to determine what eggs are fertilized based on weight and the length. So we can't draw a straight line before because if you see it is jiggled. So we can draw a curved boundary line like this. So now it is separating it. So the two groups are still distinct. We are able to separate it with a curved line. Is the region for fertilized egg and this decision region is a region for unfertilized egg. So we have the decision line. This is the decision line. And we have regions which separate the classes. Now, decision line or a decision boundary. You can call this as decision boundaries. So now that we are adding some more X to it. So now we have more data and the distribution is different. So this purchase of new chickens has made it harder to distinguish. It is even more harder to distinguish the fertilized eggs and unfertilized eggs, even with the clear. There is no clear way of drawing a line or a curve that separates them. So what to do? Now, instead of dealing with certainties, we have to deal with probabilities. So we will assume that so this shaded region is a region for fertilized eggs, and this the another region is the region for unfertilized eggs, because the majority of fertilized eggs are in this region, the majority of unfertilized eggs are in this region. So based on this one, we can assume that this region is probably the region for fertilized eggs and this region is probably the region for unfertilized eggs. Let us assume for a moment that this fertilized eggs so let us assume that the fertilized eggs are positive. So if it is positive, and we want to be very sure that we catch all the fertilized egg and we don't mind to have some false positives in our regions. So let us assume that if you have something like this, so what we can do is that we can draw a boundary line like this. So majority of the positives are captured. We have some false positives triangles in it, but it doesn't matter because our aim is to get only fertilized eggs. So the same boundary. So suppose our interest is to get unfertilized eggs. Then what we will do is that we will try to get like this, even though we get some false negatives, which are circles inside these regions, it doesn't matter that we try to get the unfertilized GX, majority of the unfertilized GX. So more than the algorithm, so it is the human factors or the business factors which is important. Here I'm saying that our main aim is to get the fertilized GX. It doesn't matter if you get false positives. So here my aim is to get the majority of the unfertilized GX in the classifier. It doesn't matter if you get it. So it is not about the algorithm or the data. We design our classifiers so based on the business factors or the human factors. So this is one thing which is needs to be understood. So later on, when you have worked with your research problems or any other real life problems, you need to understand that. So it is based on your outcome, you have to design your classifier. It is not based on any thumb rule. So next we will see about 2D multi-class classifier. So far we have been distinguishing our X in between fertilized X and unfertilized X. So this unfertilized X can be even divided into two types. One is called as a yoker, another one is called as a quitter. So there are two types in unfertilized eggs. What is this yoker? Is that this yoker is the type of egg which never get fertilized. This quitter is nothing but they are fertilized eggs, but what happens is that the embryo somehow does not grow, and sometimes what happens is that they stop growing and get dead within the shell. So these are called as quitters. So we can sell yokers, but we cannot sell quitters because quitters are susceptible for getting burst. So they get burst unexpectedly and they can spread harmful bacteria. So our goal is to identify these quitter eggs and then dispose them. So we have three categories now. Three categories of eggs. The first is called as the winners. These are viable and fertilized eggs. The second one is called as the yokers. Yokers are unfertilized eggs. The third one is called as quitters. Fetus are again, they are dead and fertilized eggs. So we have three categories. So what we have now is our multi-class classifier. We need to build a multi-class classifier because we have multiple classes. So let's imagine that the features are still the same. So we have two features. One is weight. The other one is length. So we have three categories here. So one, I can draw the circle, I can draw it as fertilized. The square, I can draw it as yolks. So we have three classes of the eggs. So all these three categories are measured using candling. So now the job is assigning one of these three classes to the new inputs called as multi-class classification. This name is usually applied to the problem where we have three or more classes. Whenever we have three or more classes, this problem is called as multi-class classification. If you have two classes, it is called as binary classification. If you have more than three or more classes, it is called as multi-class classification. So the general idea is, so any number of categories, whether it is three or more, any number of categories or labels are present. Once we have found the boundaries between these regions, so we have to associate any incoming input, we have to associate with any one of these regions. So first what we will do, we'll take the training data set. We will talk about training and testing more in this class, but given the input, so we have a new input is coming, so it is divided into regions. So we have to assign the any incoming input to any one of these classes based on the input features. So here the input features is 2D, which has two features, weight and length. Suppose imagine that we wanted to add some more features to it. So far we have two features, length and width. Suppose we are having another features like color of the egg, average circumference of the egg. Then time of the day the egg was laid. So suppose we are adding three more features. Then we will have 5 dimensions or 5 features to separate these classes into 3 classes. So we definitely can't draw a useful picture out of this 5D diagram, 5D dimension. So, but for math, it doesn't matter how many dimensions we have. So if you have 2D, we can clump the data like this and divide into regions. So if you have 5D, so what we can do is that we can draw a 5D shape, and from that 5D shape, you get split into 5 smaller dimensions, and for each dimension we can have what to say, a smaller 5D shapes.
Ma'am, you are mute again.
Am I audible now?
Yeah. 5D shape only.
Yes, ma'am.
So till 5D shape I was audible.
Yes, ma'am.
Okay. So in 2D shape, what we did, so we have a two features. So we plotted our data in the 2 dimension, and then we grouped them into regions. So any new data comes, we'll associate it with any one of the region, and then we will label it. So in 5D shape, what we can do is that we can do the same thing. So what we will have is that inside that 5D shape, we will have smaller 5D shapes where the groups are clumped together. So if any incoming thing will get attached to any one of those 5D regions to define different classes. So is it clear? In higher dimension, the same thing is going to be true. The problem is only with the multiple dimension. We cannot picturize them to see well how well it is getting attached. We need to only assume that the smaller 5D shapes will be formed into the 5D space. But whatever is happening in the 2D space will also happen in the 5D space. But only thing is that we cannot picturize it. Next, we will deal with multi-class binary classifier. So in multi-class binary classifier, there are two types which we will see. One is 1 versus rest. Another one is 1 versus 1. There are two approaches in multi-class classifier. Multi-class classifier means an input can be assigned multiple categories. So this is multi-class, multiple categories based on binary classification. So how is that possible? Is that it is possible using two approaches. One is 1 versus rest and the other one is 1 versus 1. So in one, first we will see the first one. So in 1 versus rest, what we will do is that it is a binary classifier method. It is otherwise called as 1 versus all, or it is otherwise called as 1 versus 1. One against all, or it is called as binary relevance method. So what we will do is that, suppose imagine that we have 5 categories. 5 categories of our classes. So it can the classes run from A through E. So instead of building one classifier that will assign one of those 5 labels, what we will do is that we will build 5 binary classifiers. So the first classifier will separate A versus rest. So we have 5 classes A, B, C, D, E. So the first, instead of building one classifier which can predict any one of these 5 classes, what we will do is that we will build 5 classifiers. So 5 binary classifiers we will build. The first classifier will classify A versus rest. So what it means is that a piece of data, whether it belongs to class A or not, so what we are concerned is that we are concerned only about one class. We are not paying attention to any other class. Any data comes, we will check whether this data belongs to A or the rest of the lot. So whether it is A or B, C, D, E. So if it is A, we will get as A, otherwise we will get as rest. So the classifier 2, what we will do, it will check whether the input data belongs to B or rest of the categories. The third classifier will see whether the input belongs to C or the rest of the categories. Similarly, classifier 4 will see whether the input belongs to D or rest of the categories. This one similarly E or the rest. So whether it is class E or not E to stay. Sometimes what will happen is that our classifier will belong to more than one class. So that is also possible. So what are the pros of this technique is that binary classifier can be written very easily. But the con side is that we need to teach at least 5 classifiers for a 5 class problem. So instead of using one classifier to classify 5 classes, we are building 5 classifiers to build for this task. So if you have larger number of categories with complex boundaries, the time required to run the sample will be more. Classifiers will increase along with the number of classes. So if the number of classes increases, the number of binary classifier also will increase. So this is one versus rest. We are looking at multi-class binary classifier. Next, we will see about the other thing, which is one versus one approach. So this is the second approach. So one versus one. So what is here is that it is also useful to perform a binary classifier, to do a multi-class optimization technique. So what we will do here is that it will need much more binary classifier than when compared to one versus rest. So the idea is to look at the pair of classes in our data and build a classifier for just those two classes. Suppose you have the classifier A, B. So we have classifiers. We have class A, class B, class C. So suppose we have 4 classes, class A, B, C, and D. So what we will build is that we will also build a binary classifier. Previously, what we did, we wanted to look at whether it is A or not a A. That is the classes which we took for every classifier. So here also we will take only 2 classes. It is also a binary classifier, but it will work in pairs. So suppose what to do, this will check whether it is class A versus B. This will check whether it is class A versus C. This will check whether it is class A versus D. So similarly, this is B versus C. This is B versus D. This is C versus D. So we have to, for a 4-class problem, we have to build 6 classifiers. So we first classifier is it will check whether it is class A or B for 2 classes. The second classifier will check for the classes between A and C. The third classifier will check for the classes between A and D. So this one will check between B versus C, and this one will check between B versus D, and this one will check between C versus D. So this is 1 versus 1. So how we will get to the final conclusion is this. So we will always run it through the classifiers, and then we will select the label that comes up most often. In other words, I can tell the majority of the classification votes will be taken to declare the winner. Suppose this gives you A, this gives you A, this gives you A, this gives something, something, something. So then we will understand A has a majority of the votes. So A is the final label. So we will come to the conclusion based on the majority of the votes. So this is how this classifier bit. The downside of 1 versus 1 is that it needs more number of classifiers when compared with 1 versus rest. But the pros here is that it is more appealing. It is more appealing because it provides a deeper analysis for each sample. With respect to the combination of the classes, it provides more deeper understanding. So sometimes there can be a messy overlap, but it is easier to understand with the final result. But as I said, the downside is that we need more number of classifiers when compared with one versus rest. So the number of classifier will grow up with the number of classes. So the number of classes increases, the number of classifier also will increase. So suppose imagine if you have a class and the number of classifiers, we want to tabulate it. So for 4 classes, we had 6 classifiers. For 5 classes, we need 10 classifiers. For 20 classes, we need 190 classifiers. For 30 classes, we need 435 classifiers. After 46 classes, we will need more than 1000 classes. So looking at the computer memory and the time at some point, it is more efficient to use a single complex multi-class classifier than using the binary classifier. When we have limited number of classes, this will work. But for the larger number of classes, it is better to go for multi-class classifier. Is it clear? So far what we have done is that, so we started off with what is classification. So we saw the definition of classification. We saw the various terminologies: ground truth, predicted label, classifier, sample, feature. And then we defined what is truth binary classification. Binary classification means the output is assigned with 2 labels. 2D means the number of dimensions or number of features. So the features are called as dimensions. So, and then we took an example for the classification. And then we saw how we can, we saw about the boundary method. And we also saw about the decision regions and the decision boundaries. We also saw about an example for 2D multi-class classifier. And then we saw about the different dimensions involved here. And then we also saw about multi-class binary classifier. There are 2 approaches in multi-class binary classifier. One is 1 versus rest, and the other one is 1 versus 1. So now we will briefly look at clustering. So anyone would like to recollect, because last time we did clustering. So in the previous semester, anyone would like to recollect what is clustering? Clustering is, yeah, go on.
It's for identifying subgroups in the data.
Okay, any other idea? So instead of subgroups, it is identifying different regions in the data points. So we have to classify any new sample is coming, that we need to fix up with any one of those regions. So what we have is that we have the training set. So we have to group the data into clusters or similar chunks of data. So suppose imagine that we have a data like this. So what we need to do is that we need to group into different categories. Or I would say different clusters. Categories is not a correct word, sorry. So we need to group into different regions or different clusters. So initially we can draw a curve around them, and then later on we can split the region like this. So when a new sample arrives, we will compare with each region. Whichever has a closest distance, we will place that one in the new region. So this is how clustering works. So this scheme, initially if you have labels, it is easy to cluster. Suppose if you have data without labels that fall into a category, it is called as unsupervised learning. So before I'm going to unsupervised learning, let's recap what is supervised learning. Supervised learning means what? We will have a sample and the sample will have features and also it will have labels. Features are nothing but the measurements of the sample and we will have the labels for the sample. We will give it to a classifier and then the classifier will train and then finally it will predict during the test stage. This is one thing. Unsupervised learning means we will give the samples with only the features without the labels. We'll strip off the labels and we will give it to the classifier. The classifier will identify the clusters in the data point and then it will come up with its own regions or decision regions. It will come up with its own decision regions. Whereas here, the decision regions are based on the labels. Here, the decision regions are based on the clusters. So it will identify the similar patterns or similar data points, and then it will group together. And finally, the decision region is made on this one. So how many clusters to form in an unsupervised learning? Here it is very clear. So based on the available classes, so based on the number of labels, so we have 2 types of labels or 5 classes. So based on that one, we can pick the decision regions based on the number of classes. But here, how will you decide the number of regions? We do not know that one. So for that, we would use a hyperparameter called as K. So K is a hyperparameter. It will tell us how many regions we want to build. So what is K-means clustering is the most popular algorithm. So what this K-means clustering will do is that it will create the average or the mean of the data based on K clusters. So it will develop K groups based on the average of the data points. So this is called as K-means clustering. Sometime later this course we will deal with this in detail. For now, you will understand K-means clustering means. So based on the average or the means of the data points, we will create K clusters. So where K is the hyperparameter. So what is the difference between hyperparameter and parameter? Parameter is the internal parameters which change according to the data, whereas hyperparameters are the values which the user give to the system to control its internal variables. So K is a hyperparameter which the user chooses. So the user will decide how many number of clusters has to be present. So, but there is a blessing and the curse with the value of K. So what is the advantage is that, so we know how many number of clusters are present. How many number of clusters ought to be there or have to be produced by the algorithm, we will know it. But the con or the downside is that we may not have any idea of how many clusters would be best to describe the data. Suppose if you pick fewer number of clusters, what will happen is that we may not be able to distinguish distinct classes. Suppose if you have many clusters, too many clusters, then we will end up with very similar pieces of data going into different classes. So we may not. So the same similar data point may appear in both the clusters. So there is no proper division of the classes. So this is the point of having few clusters and many clusters. The popular option is that we need to train our network several times. Each time you have to bring a different value of k. So this is called as hyperparameter tuning. So hyperparameter tuning, what we will do is that it will get the good value of k. So with the good value of k, we will select a proper value of k and then we will choose it. But it will take lot of time. Suppose imagine if you have 20 values of k, then you have to run the algorithm 20 times. So the best way is that we need to have a preview of a data. Any questions? So the best useful thing to do is that we will have a preview of the data. So we will have some kind of visualization tool prior to the clustering so that we can pick the best value of k instead of running it multiple times and then choosing what is the best value of instead of hyperparameter tuning. If you have the best value, if you look at the data and if you understand how many classes it might have, if you get some intuition before, so we can straight away fix what is the value of k, and with lesser number of iterations, we will can get the best value of k. Is it clear? So in clustering, what we saw clustering is dividing the data points into groups of similar values or clusters or regions. So in unsupervised learning, we will not have labels. In supervised learning, we will have samples along with labels. In future classes, we will do these things in detail. But now you do just understand in supervised learning, we will have samples along with their labels and we will give it to the classifier to bring out the decision region. So the number of k is fixed by the number of types of clay. So sorry, types of labels. Whereas in unsupervised learning, we will not have any labels in the data points. So the classifier itself will segregate the number of classes based on the hyperparameter k. So there is one technique called as k-means clustering in that one. And we saw what is the problem of having few number of clusters. If k value is less, what is the problem? If k value is more, what is the problem? So the best thing is to have the preview of the data so that we will find with the intuition, we can find the best number of k, which will work out for our problem. So next we will see about the curse of dimensionality. So what is dimension? Previously I told dimension is nothing but features. Dimensionality is nothing but the number of features which we have. In the previous example, we had two features, length and weight. So it is easy to draw the two-dimensional features in a two-dimensional page. But supposing if you have 5D, 5 features, we may not be able to picturize it well. So in practice, what we will think, if you have more number of features, more number of dimensions, then our data will be rich, then our classifier will perform more, or the classifier will perform better. The more the number of features we have, the better we can find the boundaries of the data. But it is true only to a certain point. After some point, what happens if you add more number of features, it will perform worst. This might sound weird, but this is what will actually happen. The more number of features, better decision boundary is not the is uh, is not the reality. So suppose in our previous example, we have two features for the example. We had length and we had weight as the features for our egg. Suppose we add some more features such as temperature of the time the egg was laid, age of the hen. Suppose other features like number of eggs in the nest. Humidity. So suppose we have 6 features. So earlier we had 2 features, 2 dimensions. So any questions? Okay. So earlier we had two features, so we were able to represent it in a 2D page like this. The two features can be represented. Now we have 6 features. So it is difficult to represent 6 features, but what we assume generally, if we have more number of features, then we will be able to get a better decision boundary. But that is not the case. So we will see how it works here. So what will happen after some point is its ability to define correct class will define. We will see with a small example here. Suppose if you have fewer number of samples. So this is fertilized eggs. This is unfertilized eggs. Suppose we have very few samples. Then we can have number of decision boundaries like this. So when the number of samples are less, we can have multiple decision boundaries. But we never know which one will work. Suppose if you are increasing the decision, number of samples in the so if your number of samples in the data points are increased, so the number of samples in the data is increased, then we can have a perfect decision boundary which separates the fertilized eggs and unfertilized eggs. So the best boundary curve we need will come with the increased number of samples in it. So if the density is high, I will put the right word. If the density is more, then we can get a perfect decision boundary. So with very few samples, we had constructed a lot of different boundaries, but we can't tell which one can do a best job. But with higher density of the samples, we can find a good boundary curve. So a good curve requires dense collection of boundary points. So what will happen if you add features to it? If we are adding features, then we have to increase the number of samples we needed. So what will happen is that then we have the number of samples will required with the increase of features will get increased. We will see how. Suppose uh, we have 10 samples, which within the interval 0 to 1, we have 10 samples. So I'm putting this 10 samples on this line segment. So we have 5 bins. We have 10 samples, which is between the range 0 to 1. We have 5 bins. So 1, 2, 3, 4, 5. So we are putting these 10 samples in the across this 5 bins. So what is the density of the sample here? So the density is given by the number of samples divided by number of bins. So the number of samples here is 10 divided by number of bins is 5. So the density per bin is 2. So per bin we will have at least 2 samples. So this is the density. This is the way in which the samples are spread out. Suppose imagine that this is for one sample. Sorry, 10 samples for one feature. And this feature is represented by one single line, a line segment. This feature could be length or weight or anything. Just for one feature, we have a single line. We have 5 bins across that line, and we found out the density of those bins by this formula. So we found out every bin has 2 samples. Suppose imagine that our sample has two features. Say length and weight. So this lines earlier we had one feature, we represented it with a line sample, line segment. So now we have two features. So we have a two-dimensional figure for it. So let us assume that every side has 5 segments. So now we can spread out our samples like this. So each side has 5 segments. So the number of bins is 5 cross 5, that is 25 bins. And the number of samples here is 10. So to find the density of the samples in this here is that. So the density is given by number of samples divided by number of bins, which is approximately 0.4. So here for each bin we had 2 samples. Here if you look, for each bin we have 25 bins. For each bin we have 0.4 sample. Here we have, previously we had one feature. Here we have two features. Let us assume that we have 3 features per sample. So we can add length, weight, and temperature. So we have 3 features. So this square can be now converted into a cube. So now I can draw these samples. So we have 3 features. So we have 3 sides. So each side has 5 segments. So totally we will have 125 bins. Samples is 10, features is 3. So since we have 3 features, we have 3 sides. Each side has 5 segments. So totally we have 125 bins and 10 samples. So now the density of the sample is number of samples divided by number of bins. So this is approximately equal to 0.08 samples per cube. So if you look at earlier, when we had one feature, we had 2 samples per bin. When we had 2 features, we had 0.4 samples per bin. But when we have 3 features, we have only 0.08 samples per cube. So when the number of features or when the number of dimension increases, our number of the density of the sample goes down. So there is no issue on to separate this one. So if you look at here, we can draw a surface like this to separate both the points. So fertilized eggs and unfertilized eggs can be separated by a surface like this. But we never know that how many empty boxes will belong to either of this side. So it is not an issue to separate this data, but we do not have a clear idea on how to separate this data. So with whatever data we have, the classifier will do a good job. It is not the fault of the classifier. It is doing its best it can do with the data. But the problem is with the density of the samples are low. The classifier just doesn't have enough information to do the job. So if you add even more features to it. So if you are adding even more features to it, what will happen is that the density will even drop tremendously. So if you have fewer number of bins, then we will have a better chance of filling them. But if you have a long number of bins, then it becomes irrelevant. The number of dimension goes up, the density will go to 0. The density will approach to 0. This is called as curse of dimensionality, because we need to look into it so that if we don't end up with a problem later on. So we need to be sure how many number of features we are choosing for a sample. So this curse of dimensionality is a serious problem. It would make all the attempts of machine learning fruitless. So what is the blessing here is that the curse is dimensionality. The what is the blessing is the structure, or non-uniformity is the structure. So another thing to be understood here is that suppose if you have features that typically measure everything. So if you have a higher dimensional space, what will happen is that the spread is not going to be uniform. If you look at here, this is a higher dimensional space. The spread is not uniform. So if you have 5 features, it is not spread all over. There are a lot of empty boxes. So it is not evenly distributed. When the dimensions are increasing, it is not going to be evenly distributed. So what we need, it is either clumped on the lower dimensional spaces, or it is clumped towards one region. It is not spread out. So all the training data or other data will generally fall into the same region. So this is an important point to note. So what is the important point is that, so curse of dimensionality is one reason why machine learning needs a lot of data. So anyone can think that why we need a lot of data. So your general assumption. I'm afraid I'm not able to hear you properly.
More for accuracy. For the accuracy, we need to increase accuracy. Accuracy of the prediction.
Okay, for accuracy. Anything else?
No, then it will fill up more of the cubes, no? Like if you have more and more data, then you, otherwise it will all get clumped in places.
So the main reason why we need is that we need enormous amount of data, because when the dimensionality increases, the density reduces. So to keep up with the density, we need more number of samples. So if the samples have a lot of measurements, lot of features, then when we go, that is a higher dimensional space, we need lot of samples to get enough density so that it will make a good boundary surface. So the decision boundary will be perfect when we have a good density of data. So that is the reason why we need enormous amount of data, because suppose if I imagine that you have a healthcare data where we have 400 features. 400 features means 400 dimension. Then think about our density in each bin. It will almost be equal to 0. So to avoid that only, we need lakhs and lakhs of images. So this is the reason. The curse of dimensionality is one reason why we need more number of data. So that the density is kept and we are able to draw a good boundary surface. So generally speaking, we need to keep our dimensions low or in an optimal level, and we should have a lot of data points so that we have the data points should be higher, the dimensions should be low, so that we have good density. And we have a better and if we have good density, we will have good boundary surface. I'm using the term surface because we are dealing with higher dimensions. We'll have good surface. Then if you have good surface, then the good chance of generalizing well with the new data. So the values for the low and the lot, it depends on the algorithm, and it also depends on what we are looking into the data. So there is no hard and fast rule that we should have this n number of dimension or we should have n number of data. There is no hard and fast rule on predicting these values. We generally take a guess on what is the performance to be, and then we'll make our internal adjustment. So we work with what we have. So is it clear? So what we did is that So in the curse of dimensionality, we saw the dimensions are nothing but the features. So when the features increases, so when the number of data is less, we have lot many options for this boundary surface. So to get a clear boundary, we need to increase the number of samples. That is the we need to increase the density of the samples. Then we saw with how when the feature increases, the density decreases. So we need to maintain a good density and we need to have a trade-off between the number of features and the density so that we are able to get a good surface. So do you have any questions?
In case of patients, the number of patients is the features or the other attributes are the features?
No.
Like
number of patients is number of samples.
Okay.
So patients, that one thing has to be very clear. I will restate it here. So the patients or the subjects is samples. The measurements which you make on the patients,
Weight, height, and
weight, height, BMI, blood sugar, BP, or whatever measurements you make on the patients is called as features. Features or dimensions. So for the same patient, you can take 10 measurements. So when you give to the classifier, you will give these 10 measurements to the classifier. So you're giving the features to that one. So samples means you have 100 patients. So in our egg problem, so the egg is a sample. The weight and the length or age of the hen or whatever it is, the feature. And then fertilized eggs or unfertilized eggs. This is the label. So there are three terminologies. One is sample, second one is feature, and the third one is label. So when we are dealing with the curse of this feature is otherwise called as dimension. When I talk about density, it is about the number of samples.
in any sample, will you have a label feature? Is label a must? I can understand you can have features, okay, and I can
Yes, ma'am.
understand to have sample, okay, that is okay. What is the role of a label in this? That I didn't understand.
Label is used in supervised learning. We can have label or we cannot have label. As you said,
Okay.
samples is a must, patient is a must, and the measurements made on the patients are features. So any data you take, we will have a sample, we will have a feature, but label is not must. Saying if you have, suppose for example, just for example, I'm saying this, you can take a patient and you can take 10 measurements, 10 blood sample measurements. So suppose if the patient is diabetic or non-diabetic, is the label you're attaching to it. So you can have the label attached or not attached. So based on the measurements made on the patient, you can say this patient is diabetic. This patient has hypertension. So that is a label you are providing it for the patient. You may or may not provide the label. So if you provide the label, it is useful in supervised learning algorithms. We will learn about these learning algorithms a bit later. But beforehand, I'm saying that if you have labels, then you can use in supervised learning. So if you don't have labels, just with the patients and the number of measurements, you can use it in unsupervised learning, where it will form the regions by itself. Yeah. Any questions? So if you don't have questions, we will meet at the next class on Friday.
Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.
Thank you.